Hello everyone. So we are on part 5 of this book, which is PDEs, also known as partial differential equations. And this is a good section for me to be on because it's actually one of my specialties when it comes to mathematical research. Differential equations in general, but of course, a subset of that is PDEs. So I'm very well versed in this stuff, and hopefully that comes through. Hopefully it seems like I'm more excited when I'm talking about it too. The Calc 3, section of this book is really interesting. I really do love Calc 3, and it's pretty hard to avoid. If you are doing any sort of research math, but in particular, if you continue the whole Calc 3, so multivariable calculus, and then you push that into research to really study kind of the ideas of Calc 3 or multivariate calculus in kind of the modern setting, it's called differential geometry. And that is not something that I research. I would love to. I think it's a fascinating subject, and I do periodically have tiny bits of my research. Like I need to draw from the theory of differential geometry to gain some of the results that I use, but it's not like the primary motivation of my research, where PDEs actually is a lot of times. So I've worked with a lot of PDEs. If you go ahead and type my name into Google Scholar, you'll find probably just about half of the papers I've published have been on PDEs. So not, technically they're like, I could tell you a lot more about it, but they're partly PDEs and partly ODEs for different reasons. But that's my research, so I'm pretty excited to be headed into this section of the book. And chapter 14 is called Modeling in the Continuum Limits. So we're going to look at modeling with ODEs and then eventually PDEs as well. And the idea of this continuum limit is that if I start, so continuum limit means starting with a lot, whatever that means. I need to put that in quotes, of ODEs taking a limit gives a PDE. That's not the only way to derive PDEs for somewhat obvious reasons. I could just start with a few partial differentials on a function and compute an equation on that. But maybe the most natural way to derive these, if I'm looking at a physical system, is via this continuum limit, where I'm going to look at a bunch of ODEs, and I'm going to take a limit and recover a PDE. So we'll get there eventually. That's section 3 into 4, kind of. So the first two sections, we're not going to really be looking at that. We're just going to be looking at the ODEs still. So even though the section is called partial differential equations, we're actually going to start here in section 14.1, which says higher dimensional ODEs. So y'all will remember the primary definition of an ODE was just something like the change in time of a quantity or a particle, or however you want to think about it, was equal to a function, perhaps of time, as well as the current position of that particle. This was your classic ODE first order that you probably studied last semester. And obviously we can add higher orders on there, but we're just going to work with first order for now because it's a little bit easier to talk about these higher dimensions in first order. If you want to, I don't think we need to talk about any higher orders right now. If you want to ask about higher dimensional ODEs and higher orders, we can definitely talk in class. But let's just focus on this classical ODE in first order. And now I'm going to give myself, instead of a single ODE, which if I erased x2 there, that looks exactly like the ODE I just drew for you. We're going to consider two of them. Okay, so we have the placement of two particles, and notably, both particles depend on each other. So this is like saying the velocity of both particles depends on the position of both. And so that's kind of tricky, right? This is, maybe we're talking about a charged system, right? If I have two electrons that are close to each other, then their velocity depends on how close they are to each other. So the closer the electrons get to one another, the more they're going to feel a repulsive force, and all of a sudden their velocity gets pushed away from one another. But if they're really far away from each other, then their velocity is going to be influenced by other factors. And we can model this sort of interaction of the velocity of two particles as they interact with a function of both, right? So the velocity of particle 1 is some interaction of particle 1 and 2 modeled by f, and the velocity of particle 2 is an interaction of 1 and 2 modeled by a different f. And there's nothing special about just having two particles around. We can have a lot of particles. So we could jump up to any number. So here it says a system of ODEs is a collection of differential equations of various order, and we call the system coupled if the equations depend on one another. So long as like at least one of the particles is interacting with another particle under this function that has both of them, then we call that a coupled system. And like I was saying before, we could add an x3 into here, we could add an x4 into here, dot, 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 and then we would gain like an x3 in that function, an x3 in that function, x4 in both of them too. And so the system, 400 electrons, this is why, some proteins or something are really hard to model on a computer, because we're just dealing with so many electrons which all depend on each other. And so it gets really, really hard to model these on a computer. But that's why they're important, because electrons do interact with each other in very noticeable ways. And I keep using electrons, but of course this can apply to all sorts of other particles which have any sort of influence over one another. I mean, this is economics theory is the same thing, right? When the price of one commodity influences the price of another, right? The price of oil influences the price of gas, which influences the price of your food, because the trucks which are transporting your food need to use gas to transport it, and so you have a lot of influence of one change on other changes, and vice versa. So this is why we end up with inflation. So these sorts of systems show up everywhere. And actually, this is something interesting that I wanted to comment on, because the book mentions this right here, this Lorentz 96 model, and it says it represents atmospheric dynamics along lines of latitude. I'm really surprised that Colin knew about this model. It's not terribly common, but it was actually part of my dissertation research, so I'm kind of impressed that Colin knew about it. It's used a lot, like, they say atmospheric dynamics here. It's used a lot in like meteorology, but if you're not in meteorology, I wouldn't exactly know a reason why you would come across it. It's a nice little toy system for chaos, so maybe that's why you came across it. But if you look at the Wikipedia page, it's really tiny, and so I'm kind of impressed that he knew about it. And it's close to my heart, because I worked on it pretty substantially for a couple of years for my dissertation. So that's kind of quaint. And the atmosphere is another case where the velocity or the air temperature at one spot is going to influence the air temperature somewhere else in the atmosphere, because, as we all know, heat moves around. So that's how we also have these systems of coupled equations. Okay, so let's scroll down a little bit and maybe look at a nice example of one of these. This is called the SIR model in ecology, and the letters correspond to susceptible, resistant, and infected. So this is actually incredibly important. This was kind of the classical first choice for modeling COVID back at the beginning of the COVID pandemic. All of the epidemiologists were using this model, at least in the early stages, because we just didn't know how it was going to behave. And this is kind of, in some cases, the simplest system which can model the interactions of a virus or anything else that's infectious through a population. And so what the model is saying is that the change in the people who are susceptible depends on the current number of people who are susceptible plus the number of people who are infected, which makes a lot of sense, right? Because the more people that you have infected, the fewer susceptible you're going to have, because once you're infected, you're actually no longer susceptible. So that's why we have a negative sign there. Because you're either infected and you die, or you're infected and you recover, and then you don't get the disease again. So the more infections there are, actually, the fewer susceptible people, because susceptible is classified as the people who haven't yet been infected. And so it depends on both the infected people and the susceptible people. The change in the infected people is kind of, there you can see it's the inverse of the susceptible, right? So if somebody used to be susceptible and they're no longer susceptible, there's only one reason for that, and that's that they got infected. But we also have this term here, where actually the rate of the people infected gets reduced by the total number of people that are currently infected as well, because if people are currently infected, those people can't get infected again. So they're going to reduce the rate of infection, but then the resistant one is exactly proportional to the people who have been infected, because that's the only way to gain resistance. This would be before vaccines, of course. So before vaccines, the only way to gain resistance is to be infected. And not everybody who's infected necessarily gains resistance. That's what this parameter gamma kind of describes. It says, okay, if gamma is like 0.9, maybe 90% of the people who are infected gain resistance out of the infection. But some people won't, and they can possibly be reinfected. So this is like a really nice model. It's relatively simple. It's what we call nonlinear, because we do have multiplication between these two terms, but it's very simple, and definitely your computer can model this really quickly, which is why it was so useful for the epidemiologists at the beginning of the pandemic. So talking about the system SIR, we'll notice that we have three different variables which all depend on things. It makes our life easy easy to group these into a vector. The reason being, we can either think about these as three separate equations, which have an influence over one another, or we can think about it as a single equation, which is just evolving in three-dimensional space. And that makes our life easier because we have all of the tools of Calculus 3, or this past section of the book, at our disposal when we think about these as vectors. When we think about them as kind of three independent entities, we don't gain those nice tools that we were just working on. So that's what the book is describing here. It says, okay, hey, let's reevaluate X if I have maybe n different systems or n different particles that I care about or whatever. I'm going to group them all into a vector. I'm going to call it vector X. Okay, so vector X contains the information of all of the system, and we call X the state. Okay, so when we group things into a vector, we call that the state of the system, and it has n dimensions. We can also, if I jump back up, maybe up here, so if I group x1 and x2 together as a vector, that's like me taking that and put it in a vector, I can put the right-hand side in a vector as well, right? Because there's no reason I can't call this vector x dot, and there's no reason I can't call this vector f, and then vector f right there, that's vector x, and then it depends on t. And so I can make kind of a condensed version of my system just by thinking about the change in a vector is dependent on a vector valued function, also known as a vector field. So maybe we should start to change our notation from f to v and think about it as a vector field. But all this is saying is that the change in a vector equals a vector field, which inputs the change in the vector and possibly time. So if we jump down here, that's what it's showing us right here. Okay, so that we're going to relabel my system of functions, which were each one-dimensional, even though they had multiple inputs. We're just going to group those together in a vector as well, and we gain this beautiful vector equation that's just the change in a vector equals the vector field. We can also have an initial condition, right? If we group initial conditions together, grouping initial conditions into a vector. You'll recall your initial conditions, at least in one dimension from the previous semester. Each one of the differential equations is itself going to have its own initial condition, and then we can just group them all into a vector as well. So really, we just have a initial value problem, which is now vector valued. Okay, so that's all that I actually have for today. It was a pretty brief one. I just wanted to kind of describe these from a distant perspective, and then we're going to actually work with these a little bit more in the next section. So I'll see you in class. Bye.